Two measurements, two different answers, same universe. For decades, astronomers have had two completely independent methods to calculate how fast the universe is expanding. Both methods are rigorously tested. Both are backed by generations of careful data. Both should give the same number. They do not. And every new instrument scientists build to resolve the disagreement makes it worse, not better. That tension has a name, the Hubble tension, and it is just one branch of a larger problem now unfolding across cosmology. Because in July of 2022, a space telescope opened its mirror and began staring into the deep past, and what it found has been quietly rewriting the story of the cosmos ever since. The James Webb Space Telescope was launched on Christmas Day of 2021 after decades of engineering, setbacks, and anticipation. Its primary mirror spans 6.5 meters. It operates in the infrared, which allows it to detect light that has been stretched by the expansion of space itself. Light from galaxies so distant their original ultraviolet glow has been redshifted into the invisible infrared range. No telescope before Webb could see this far with this much clarity. When the first deep-field image loaded onto the screens at the Space Telescope Science Institute in Baltimore in July of 2022, the room went silent. The image showed a patch of sky smaller than a grain of sand held at arm's length. Inside that patch were thousands of galaxies. Some glowed in familiar shapes nearby. Others at the edges of the image had their light bent and distorted by the gravity of massive galaxy clusters in the foreground. A phenomenon called gravitational lensing that effectively gives Webb a free magnifying glass. But what stunned the scientists was what they found when they began measuring the most distant objects. Those galaxies, billions of light years away, were not behaving according to plan. According to every model of cosmic evolution built over the last 4 decades, the earliest observable era of the universe should look primitive. Gas clouds barely beginning to condense. Faint proto-galaxies just starting to gather their first stars. Nothing organized, nothing massive, nothing mature. The expectation was that deep observations would show a universe in its infancy, a dim, disorganized cosmic nursery. What Webb revealed instead looked like a fully built city photographed from orbit. Galaxies that should have been faint smudges appeared bright, organized, and massive. Their light had traveled for over 13 billion years, meaning we were seeing them as they existed when the universe was barely a few 100 million years old. And they looked far too complete, far too heavy, far too structured for their age. One scientist later described the feeling as being handed a baby photo and seeing an adult face staring back. A senior astronomer told reporters that the early results had triggered a quiet panic inside the community. Models constructed over 40 years suddenly appeared broken. Predictions made in peer-reviewed papers from the previous decade no longer matched what the telescope was showing. Some research teams stayed up through the night running simulations, trying to recreate the observations. The simulations failed to reproduce what Webb had found. Then the second wave of shock arrived. Webb did not find 1 or 2 anomalous early galaxies. It found dozens, then hundreds. Each one appeared more structurally advanced than its age should allow. Some had clear, organized shapes. Some contained heavy elements like iron and oxygen, which require multiple stellar generations to produce. Some showed evidence of central black holes already feeding on surrounding gas at the centers of galaxies that should barely exist yet. This was not a small revision to the cosmic timeline. This was a structural crack in the foundation of modern cosmology. Inside private scientific meetings, the question shifted. It was no longer whether the standard model needed updating. The question became how severely it was broken. To understand why that question is so serious, consider what the standard model actually says. The lambda-CDM model, shorthand for lambda cold dark matter, describes the universe as a system that began with the Big Bang approximately 13.8 billion years ago, expanded rapidly, cooled slowly, and gradually built structure from the bottom up. Small things formed first. Tiny clumps of gas gathered under gravity. Those clumps grew into small proto-galaxies. Those proto-galaxies merged and accumulated mass over billions of years to become the massive spiral and elliptical galaxies we see today. This model is not an abstract guess. It is built on a mountain of observational evidence. It explains the distribution of galaxies across the sky, the temperature variations in the ancient cosmic background radiation, the abundance of elements in the universe, and the large-scale structure of the cosmic web. It is one of the most tested frameworks in all of science, and Webb is challenging it on almost every front. In early 2023, a team of astronomers led by researcher Ivo Lab published a paper that detonated quietly inside the field of cosmology. They had analyzed Webb data and found 6 galaxies that could not easily be explained by any existing model. The research community gave them an unofficial name that spread quickly through scientific circles. They called them the universe breakers. The reason was straightforward. These 6 galaxies were enormous. They appeared in a cosmic era when the universe was between 500 and 700 million years old. At that age, according to the standard model, the largest galaxies should contain the stellar mass equivalent of a few billion suns. The universe breakers contain tens of billions of solar masses. Some estimates pushed past 100 billion. That is roughly the total stellar mass of the Milky Way today, packed into objects that should still be in their infancy. The math that followed was deeply uncomfortable. To produce that much stellar mass in such a short time, gas would have needed to convert into stars with almost perfect efficiency. No wasted material, no leftover gas, no energy blown away by radiation. Real galaxies do not behave this way. Star formation is messy, slow, and inefficient. Most of the gas available in a galaxy at any given time gets scattered by stellar winds, supernova shockwaves, and the intense radiation of newly formed massive stars. The early universe, which was hotter and more violent, should have been even less efficient at forming stars, not more. Some scientists tried to explain the universe breakers away. Could they be supermassive black holes glowing brilliantly and mimicking galaxy brightness? Could they be multiple overlapping galaxies seen as one? Could there be errors in the distance measurements? Each alternative was examined carefully. A few of the 6 galaxies did turn out to have unusual properties that softened their contradictions slightly, but several remained stubbornly difficult to explain. One became particularly famous in astronomical circles. It appeared to contain roughly as many stars as the Milky Way, but it existed when the universe was only 5% of its current age. No clean physical explanation for that has been produced. The implications spread rapidly through the field. If even one of these galaxies is genuine, then early cosmic growth must operate under physical rules that have not yet been discovered. Some scientists openly suggested that dark matter must behave differently than assumed. Others proposed that the early universe experienced moments of intense gravitational collapse, brief cosmic boiling points, where matter accumulated at rates that modern equations cannot describe. A few proposed something even stranger, that the very first stars were hundreds of times more massive than typical stars today, and that they collapsed almost immediately into black holes, which then attracted surrounding gas at extraordinary rates, building galactic structures in a fraction of the expected time. This idea remains highly debated, but the fact that it is being seriously discussed at all reveals how uncomfortable the situation has become. The universe breakers are not isolated curiosities. They belong to a growing pattern, because when astronomers followed the thread of anomalies Webb was producing, they kept finding more threads. Spiral galaxies are some of the most beautiful and recognizable objects in the cosmos. The Milky Way is one. Andromeda is another. They have flat rotating disks, sweeping arms, dense central bulges, and a graceful stability that makes them look ancient and organized. For decades, astronomers believed spiral galaxies were the product of a long, careful construction process. Gas had to cool and settle. Stars had to accumulate into a disk. The disk had to stabilize against disruption. Spiral arms required gravitational waves to roll through the structure for billions of years. The standard model placed the earliest true spirals at roughly 6 to 8 billion years after the Big Bang. Anything earlier should have been chaotic and formless. Webb destroyed this timeline. When the telescope examined the early universe, it found galaxies with unmistakable spiral structure as far back as 1 to 2 billion years after the Big Bang. These were not faint suggestions of disks or ambiguous smudges that required interpretation. They were full, organized rotating disks with clear structures, multiple arms, and central bulges. Some looked nearly identical to spiral galaxies in the modern cosmos. A British astrophysicist working on the data described the discovery as finding a fully built city in what was supposed to be an uninhabited wilderness. The number made the problem even sharper. A team at the University of Manchester ran the analysis and found that more than half of the galaxies studied in the early universe showed clear disk shapes. According to traditional simulations, the fraction should be close to zero. Disk galaxies require calm, stable environments to form. The early universe was supposed to be the opposite, violent, hot, and constantly disrupted by mergers. Yet the disks appeared in abundance, organized and rotating, as if billions of years of settling had already occurred. Several theories exist to explain this. Cold dark matter halos may have formed faster than expected, providing stable gravitational scaffolding earlier. Early gas may have been cooler and denser in some regions, allowing it to settle into thin rotating layers more quickly. Some researchers even proposed that mergers in the early universe were somehow gentler than assumed, allowing disks to survive and organize rather than being torn apart. None of these ideas fully resolves the problem. Simulations still cannot reproduce what Webb is showing. The early universe was not the clumsy, chaotic infant the standard model predicted. Something allowed galaxies to grow up far faster than they should have. And alongside the disk problem, another anomaly was quietly building into a crisis. The Hubble tension has been troubling cosmology for years, but it became sharper every time a new instrument was brought to bear on it. The question at its heart is simple: how fast is the universe expanding right now? The answer, called the Hubble constant, should be a single number. Instead, different measurement methods return different values, and the discrepancy refuses to close. The first method uses the cosmic microwave background, the ancient light released about 380,000 years after the Big Bang, when the universe first became transparent. Satellites like Planck have mapped this ancient radiation with extraordinary precision. By analyzing its temperature variations, scientists calculate how fast the universe should be expanding today, based on its state at that very early moment. This method gives a Hubble constant of approximately 67 kilometers per second per megaparsec. The second method uses objects in the nearby modern universe. Astronomers measure Cepheid variable stars, which pulse with predictable rhythms that reveal their true brightness. By comparing true brightness to apparent brightness, they can calculate distance. They also use type Ia supernovae, which explode with consistent luminosity and can be used to measure vast cosmic distances. These measurements of the local universe give a Hubble constant of approximately 73. Both methods are among the most carefully checked in all of astronomy. Both should agree. They do not. And the difference of 6 units in those numbers, 67 versus 73, represents a fundamental contradiction. The universe cannot have two different expansion rates. Either something is wrong with how we measure the ancient universe, or something is wrong with how we measure the nearby universe, or something is deeply wrong with the model that connects the two. When Webb launched, many hoped it would resolve the tension by providing the most precise Cepheid measurements ever made. Webb did deliver sharper images and cleaner data. The tension remained. The local universe still appears to expand about 8 to 9% faster than the early universe predicts it should. This discrepancy is not measurement error. It has survived every new instrument and every new analysis, and it is pointing towards something fundamental that the standard model may be missing. Several explanations have been proposed. Early dark energy is one, an unknown form of energy that existed in the first few 100,000 years after the Big Bang and pushed space to expand slightly faster before fading away. If true, this would shift the early expansion rate upward and could bring the two measurements into agreement. But early dark energy has never been detected, and adding it to the model requires introducing an entirely new ingredient to the cosmic recipe. Another proposal involves modifying gravity at cosmic scales. If gravity behaves slightly differently across vast distances than our equations currently describe, the expansion history of the universe could differ from predictions. This idea gains more attention every year. A third possibility is simply that something important is missing from the model itself, an ingredient so fundamental that its absence causes everything else to be slightly wrong. The Hubble tension matters beyond the expansion rate, because the Hubble constant is directly tied to the age and size of the universe. If the constant is wrong, the timeline is wrong. And if the cosmic timeline is wrong, then many of Webb's most troubling discoveries, galaxies too massive, black holes too large, heavy elements too abundant, might look less impossible simply because the universe has had more time than we believe. The connection between the Hubble tension and the galaxy anomalies is not a coincidence. Both are telling the same story from different directions. The universe's history appears to be measured incorrectly. Black holes make this even clearer. A supermassive black hole is one of the most extreme objects that physics allows. At the center of nearly every large galaxy sits one of these invisible monsters, regions of space where gravity is so concentrated that not even light can escape once it crosses the event horizon. The largest of them contain billions of times the mass of our Sun. The textbook story of how they grow begins with stellar remnants. Large stars explode. Their cores collapse into stellar mass black holes weighing between a few and a few dozen solar masses. Over billions of years, these black holes grow through mergers and accretion, drawing in surrounding gas and dust until they accumulate enough mass to become supermassive. This process has a fundamental limit built into the physics. A growing black hole releases enormous amounts of radiation as matter falls in. That radiation pushes outward, resisting further infall. The balance between these forces defines a maximum growth rate called the Eddington limit. Even at this maximum rate, a small black hole needs an enormous amount of time to grow into a billion solar mass giant. Webb found billion solar mass black holes in galaxies that existed less than 700 million years after the Big Bang. The math does not work under standard assumptions. There is not enough time. Even starting with the largest plausible seed black holes from the collapse of massive early stars, even assuming continuous Eddington rate accretion with no interruptions, the numbers do not produce monsters of this scale in the available time window. Researchers have described this as a brick wall, not an anomaly, not a marginal contradiction, but a direct confrontation with the limits of what current physics permits. Several explanations are being considered. One is direct collapse. The idea that in certain regions of the early universe, enormous gas clouds skip the star formation stage entirely and collapse straight into black holes weighing thousands to millions of solar masses. These objects, sometimes called direct collapse black holes, would have provided a massive head start. No stellar intermediate, no slow buildup, just a sudden leap to enormous initial mass followed by rapid growth. This idea is theoretically coherent, but has never been directly observed. Another explanation involves super-Eddington accretion. If early gas was dense enough and cool enough, matter might have fallen into black holes at rates exceeding the standard limit without triggering the usual radiation-driven blowout. Some simulations show this is possible under extreme conditions. Whether those conditions actually existed in the early universe is still debated. A third, more speculative proposal involves primordial black holes, objects that formed not from the collapse of stars, but from density fluctuations in the very first fractions of a second after the Big Bang. If these relics exist, they could have provided ready-made seeds that bypass the entire stellar evolutionary pathway. This idea has a long history in physics, but has never been confirmed. Webb's findings are causing it to receive renewed serious attention. Whatever the mechanism, the implication is unsettling. The early universe appears to have been building supermassive black holes far faster than current physics comfortably allows. And those black holes may not have grown alongside their galaxies. They may have come first. This picture became even stranger when Webb identified what researchers began calling the little red dots. Scattered across Webb's deep field surveys are tiny, intensely red glowing points that initially looked like ordinary background galaxies. As astronomers began studying them in detail, they became increasingly puzzling. Their colors did not match any familiar category of object. Their compactness was extreme. They appeared as single points, yet they radiated with energies that should require enormous luminosity. They appeared most frequently in galaxies that existed when the universe was between 500 million and 1 billion years old. Spectroscopic analysis revealed the source of the strangeness. Many of these little red dots appear to host supermassive black holes, not small ones, massive ones, carrying weights that current theory says should not exist at that age. In some cases, the central black hole appeared to weigh as much as the entire stellar mass of the host galaxy. In the modern universe, supermassive black holes typically account for about 0.1% of their galaxy's stellar mass. The relationship is tight enough that astronomers treat it as a reliable cosmic law. Webb's little red dots shatter that law completely. Some of these early black holes are 100 times more massive relative to their galaxies than they should be. This means the early universe may have been growing black holes before galaxies could catch up, an inversion of the relationship that modern cosmology has always taken for granted. Hundreds of little red dots have now been cataloged. They were common in the early universe. Whatever they are and whatever process produced them, they were not rare accidents. They represent a pattern, and that pattern points to a universe whose earliest chapter was dominated by extremes that current models did not predict. The chemistry of the early universe is equally difficult to explain. Every atom heavier than helium was forged inside stars. This is one of the most well-established principles in astrophysics. Hydrogen and helium emerged from the Big Bang itself. Everything heavier, carbon, oxygen, iron, silicon, was produced in stellar cores over millions or billions of years, then scattered across space when those stars exploded as supernovae. A first generation of stars must form, burn, and die. Their remnants must cool and mix with surrounding gas. A second generation then forms from this enriched material. Only gradually does the cosmos accumulate meaningful concentrations of heavy elements. According to standard models, this enrichment process requires at least 1 to 2 billion years. Webb found heavy elements in galaxies that existed less than 500 million years after the Big Bang. Spectroscopic analysis of ancient distant galaxies has revealed traces of iron, oxygen, carbon, and silicon at concentrations that approach those found in galaxies in the modern universe. A team in Germany repeated their measurements multiple times. The data held. The early universe was chemically far more advanced than any model predicted. Something forged those heavy elements at extraordinary speed and distributed them widely. But the suspected source of that rapid enrichment is itself mysteriously absent. The first generation of stars, called Population 3 stars, has never been definitively detected. Population 3 stars are theoretically essential to the cosmic story. Forming from pure hydrogen and helium with no heavier elements to cool the collapsing gas clouds, these first stars were predicted to be enormous, possibly hundreds of times the mass of the Sun. They would have burned at extreme temperatures, generated intense ultraviolet radiation, lived only a few million years, and then exploded as massive supernovae, seeding the universe with the first traces of heavy elements. Everything that came after, planets, life, complexity, descends in some way from this first generation. Webb was expected to find them. It has not. Years into its mission, Webb has searched the earliest galaxies for the spectroscopic signatures of Population 3 stars. Those signatures are distinctive, specific patterns of ionization in surrounding gas that reflect the extreme temperatures of these ancient giants. The signals have not appeared, or when they do appear faintly, they are far weaker and rarer than models predict. This absence is one of the most quietly disturbing puzzles the telescope has produced. If Population 3 stars existed in the form models predict, the early universe should be full of their signatures. Webb should be detecting them routinely. The silence suggests either that these stars were very different from the theoretical prediction, smaller, cooler, and less distinctive, or that the early universe's first stellar generation followed a pathway that current astrophysics does not adequately describe. And yet the heavy elements are there. Something produced them. Something burned through an early universe that we cannot yet see and left behind a chemical fingerprint in galaxies that should have been pristine. The dust problem makes this even harder to dismiss. Cosmic dust, microscopic grains of silicates, carbon, and metal compounds, is essential to galaxy evolution and planet formation. Without dust, rocky planets cannot condense. Without rocky planets, the conditions for complex chemistry and life become far more difficult to achieve. Dust is also a product of stellar evolution. Stars must form, age, and shed material. Only after multiple stellar generations does dust accumulate in meaningful quantities. Standard models estimate that significant dust production requires at least several 100 million years, and full enrichment takes more than 1 billion. Webb found dust-laden galaxies that existed only a few 100 million years after the Big Bang. Some of these ancient galaxies showed so much dust that their light emerged heavily reddened and attenuated, behavior typically associated with mature, chemically evolved galaxies in the modern cosmos. The dust was not a trace. It was abundant, widespread, and real. A team in the Netherlands exhausted every alternative explanation before accepting the conclusion. The dust was genuinely there, in concentrations that should not have been possible at that age. Whatever produced it must have worked at extraordinary speed. The implication is significant. If dust formed early, then the conditions for planet formation also arose earlier than anyone imagined. The universe was laying the groundwork for rocky worlds and potentially for life far sooner than the standard model suggests. Connected to this is another uncomfortable question. Why does the early universe look so organized at large scales? The cosmic web is the largest known structure in the universe. Galaxies are not randomly distributed across space. They cluster along enormous filaments of gas and dark matter that stretch across hundreds of millions of light years, connecting into vast sheets and dense nodes where galaxy clusters form. The overall structure resembles a three-dimensional spiderweb of almost incomprehensible scale. The formation of this structure is one of the great slow processes of cosmic history. Dark matter condenses first. Gas follows. Galaxies accumulate along the dark matter filaments over billions of years. Webb has found these filaments in the early universe, in an era when the cosmic web should barely have begun to form. Long filaments connecting galaxies across millions of light years appeared in regions where the universe was only a few 100 million years old. A team at Tokyo University confirmed that these filaments were already organizing galaxies into the scaffolding of the cosmic web during an era when the standard model predicts only small, disorganized clumps should exist. The universe was building its skeleton before its individual pieces were fully grown. It was weaving its large-scale structure together, far faster than the physics of gravitational collapse comfortably allows. Several groups have noticed that some of these filaments appear aligned in unusual directions, patterns that seem to echo the rotation asymmetry discovered in galaxy spin distributions. When researchers examined large samples of galaxies across enormous distances using both Hubble and Webb data, they found a puzzling asymmetry. Galaxies are supposed to spin with equal numbers, rotating clockwise and counterclockwise, as seen from any given vantage point. The universe is supposed to have no preferred direction, no cosmic handedness. But the data reveals a subtle but persistent imbalance. More galaxies appear to rotate in one direction than the other. The asymmetry is small but statistically real, surviving multiple independent analyses and different sampling techniques. A team at Kansas State University has been investigating this for years. Their conclusion is that the asymmetry is not a measurement artifact. Something appears to be breaking the symmetry that the standard model demands. The universe may have a slight rotational preference, a cosmic tilt that influences galaxy formation on the largest scales. The most dramatic interpretation is that the universe itself may have a very slow, large-scale rotation. If the cosmos is spinning on some enormous axis, galaxies forming inside it would inherit a directional bias. This idea has historically been dismissed because it conflicts with the assumption of isotropy, the principle that the universe looks the same in every direction. But the data is making that assumption harder to defend. Alternatively, subtle directional features in the cosmic microwave background, features that were previously dismissed as statistical noise, may be real. Webb's observations are forcing astronomers to revisit these anomalies with fresh eyes. The cosmic microwave background itself is now under new scrutiny. For decades, the cosmic microwave background has been considered the cleanest and most reliable snapshot of the early universe. It is the ancient light released approximately 380,000 years after the Big Bang, when the cosmos first became cool enough for electrons and protons to combine into neutral hydrogen. Before that moment, the universe was opaque. After it, light could travel freely for the first time. That light, cooled and stretched by 13 billion years of cosmic expansion, now permeates all of space as microwave radiation. Its temperature variations, mapped with extraordinary precision by satellites like Planck, encode information about the universe's composition, geometry, and early structure. But Webb's findings are creating a growing tension with what the cosmic microwave background predicts should follow from it. The growth of galaxies, the emergence of supermassive black holes, the distribution of heavy elements, the structure of the cosmic web in the early universe. All of these are happening on a timeline that does not precisely match the predictions derived from the cosmic microwave background. A team in Germany ran a comparative analysis and found that reconciling the two signals requires either revising how the cosmic microwave background is interpreted or accepting that the standard model is missing something fundamental that affects cosmic evolution between the moment of recombination and the galaxy's Webb is now observing. Some researchers have proposed that the cosmic microwave background contains hidden patterns that previous analyses did not recognize. Machine learning tools applied to the data have begun uncovering subtle features that standard models did not predict. Others suggest that if the universe has genuine directional asymmetries, the rotational preference seen in galaxies, then the cosmic microwave background should also show them, and certain faint alignments in the data that were previously dismissed as noise may in fact be real signals. The cosmic microwave background was once thought to be the bedrock of modern cosmology, the cleanest, most unambiguous data source available. Webb is contributing, indirectly but powerfully, to a growing realization that even this bedrock may rest on assumptions that need revision. While Webb has been challenging cosmological models at cosmic scales, it has simultaneously been producing extraordinary discoveries in domains far closer to home. One of the most significant involved a planet called WASP 39b. It is a giant world roughly the size of Saturn, located approximately 700 light-years from Earth. It orbits so close to its host star that its year lasts only about 4 Earth days, and its dayside temperatures exceed 800 degrees Celsius. Astronomers had studied it many times before with previous telescopes, but Webb saw it in a way no instrument had managed. The analysis Webb produced on WASP 39b was the most detailed atmospheric chemistry profile ever made on a world outside our solar system. It contained a discovery that set the field of exoplanet science in a new direction. Webb detected sulfur dioxide in the planet's atmosphere. This was a first. No previous telescope had confirmed the presence of this molecule on another world. But the significance was not merely the detection itself. It was what the detection revealed about the mechanism producing it. The sulfur dioxide was forming through photochemistry, the process by which intense stellar ultraviolet radiation breaks apart molecules and drives new chemical reactions. On Earth, photochemistry operates in the stratosphere. Webb had confirmed it happening on another planet for the first time in history. This means exoplanet atmospheres are not passive layers of gas. They are dynamic, chemically active environments shaped by radiation from their host stars. The implications for the search for life are direct. Photochemistry plays a central role in maintaining the conditions for biology on Earth. Knowing that it occurs on other worlds opens new avenues for understanding which planets might be capable of hosting life. Beyond sulfur dioxide, Webb detected water vapor, carbon dioxide, carbon monoxide, sodium, and potassium in WASP 39b's atmosphere. It mapped their distributions by altitude. It revealed cloud structures and wind patterns. It detected haze layers high above the planet's surface. The level of detail was unprecedented. Some chemical abundances appeared at unexpected levels, and some reactions were proceeding faster than models had predicted. Each new measurement generated new questions. The methods demonstrated on WASP-39b can now be applied to other worlds, including smaller, cooler, potentially habitable ones. The era of detailed exoplanet atmospheric chemistry has arrived earlier than most scientists anticipated. Another world drew even more attention when Webb turned its instruments toward it. K2-18b is a planet approximately 120 light-years from Earth, orbiting a small red dwarf star. It is about 2.5 times the size of Earth and nearly 9 times its mass, a category of planet called a sub-Neptune, common throughout the galaxy, but poorly understood because no such planet exists in our own solar system for comparison. K2-18b is believed to be a Hycean world, a hydrogen-rich atmosphere covering a deep global ocean of liquid water under exotic high-pressure conditions. Webb's analysis of its atmosphere detected methane and carbon dioxide clearly. Then it found something that stopped the scientific community cold: a tentative signal of dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by marine phytoplankton. It is released in enormous quantities by ocean microbes and plays a role in cloud formation and atmospheric chemistry. There is no known geological or chemical process that produces dimethyl sulfide in significant amounts without biology. If the signal from K2-18b is real, it would be the most striking potential biosignature ever detected on another world. The research team was careful. They stated clearly that the detection was not confirmed, that the signal was weak, that alternative chemical explanations on a Hycean world might exist, and that more observations were required before any conclusions could be drawn. They did not claim to have found life, but they had found something that demands a serious explanation. The question of whether K2-18b's atmosphere contains a molecule that on Earth is a signature of biology is now one of the most actively investigated questions in science. Several major observing campaigns are now focused on this planet. The coming years will either strengthen the signal or reveal it to have a non-biological explanation. Either way, the discovery marks a turning point. The search for biosignatures has moved from theoretical discussion to active data collection. Within our own solar system, Webb has also provided the clearest views, yet of some of the most intriguing candidates for life: the icy moons of the outer planets. Europa, the moon of Jupiter, is covered in a thick shell of ice beneath which lies a liquid ocean, estimated to hold twice as much water as all of Earth's oceans combined. Its rocky seafloor may host hydrothermal vents similar to those found in Earth's deepest ocean trenches, where life thrives without sunlight. Webb detected carbon dioxide, water vapor, and salts on Europa's surface, chemical signatures suggesting that material from the subsurface ocean has reached the surface, leaving behind detectable traces. Enceladus, the small icy moon of Saturn, is famous for its geysers, towering plumes of water vapor and organic molecules that erupt from cracks in the ice and connect directly to the subsurface ocean. Webb analyzed these plumes in new detail, detecting water, methane, ammonia, and complex organic molecules. The chemistry is more intricate than previously realized, hinting that the ocean beneath the ice may be a chemically active environment with the ingredients necessary for biology. Ganymede, the largest moon in the solar system, was also examined. Webb detected water ice and salts on its surface, refining the picture of how its internal ocean, which may be even larger than Europa's, interacts with its outer crust. Triton, the retrograde moon of Neptune, which orbits its planet backwards, strongly suggesting it was captured from the outer solar system, received attention as well. Webb produced detailed chemical maps of Triton's surface, revealing nitrogen geysers and organic molecules alongside features that suggest subsurface activity. Some regions appear geologically dynamic in ways that hint at an internal liquid layer. A team at Johns Hopkins University, reviewing Webb's icy moon data, concluded that subsurface ocean worlds may be far more common in the cosmos than previously believed. The definition of habitability is expanding. For decades, the search for life focused primarily on warm, sunlit, rocky planets. Webb is showing that frozen worlds with hidden liquid interiors may represent an equally valid pathway. Farther out in the cosmos, Webb resolved something extraordinary, a single star burning at the edge of the observable universe. Its name is Earendel. The light now reaching Webb began its journey when the universe was less than 1 billion years old. It has traveled for more than 12.9 billion years. Under normal circumstances, no telescope could ever resolve an individual star at this distance. Stars are far too small compared to the distances involved. What makes Earendel visible at all is a massive galaxy cluster sitting directly between Earth and the star. Its gravity acts as a natural lens, bending and amplifying Earendel's light into a thin streak of detectable signal. This effect, gravitational lensing, gave Webb a window to something that should have been forever invisible. Webb's observations suggested that Earendel may be a binary system of two giant blue stars orbiting one another, together potentially weighing many dozens of solar masses. Stars from this era of the universe are believed to have formed from gas with very few heavy elements. Studying Earendel directly offers a rare opportunity to test that assumption. Its spectrum could reveal the chemical composition of stars from the cosmic dawn, potentially confirming or challenging models of the earliest stellar generation. A team at the University of Cambridge has been carefully analyzing Earendel's light. Some early indications suggest the star has properties unlike anything found in the modern Milky Way: extreme temperatures, intense radiation, and a spectral character that seems genuinely foreign compared to today's familiar stellar populations. As the most distant single star ever observed, it may carry information about the universe's first billion years that no other source can provide. Earendel will not hold this record forever. Webb is expected to discover additional lensed individual stars from the early cosmos, but it is the first, the pioneer, and its existence proved that even single stars from the cosmic dawn can be made to speak. All of these discoveries, the overmassive early galaxies, the premature spiral disks, the impossible black holes, the too early heavy elements, the missing first stars, the anomalous galaxy spins, the unexplained rotation curves, the early cosmic filaments, the atmospheric chemistry of distant worlds, are accumulating into something that cannot be addressed one anomaly at a time. They form a pattern. Each individual finding might be explained by some specific adjustment to the standard model, a slightly different dark matter behavior here, a revised stellar formation efficiency there, a measurement calibration refinement somewhere else. But when these anomalies are examined together, the picture that emerges is not one of a model in need of minor tweaks. It is a picture of a model whose foundational assumptions may be incorrect in ways that have not yet been identified. The standard model of cosmology, lambda-CDM, remains the most successful framework ever developed for understanding the large-scale structure and evolution of the universe. It correctly predicts many things: the distribution of galaxies across the sky, the abundance of light elements from nucleosynthesis, the geometry of the cosmos, the structure of the cosmic microwave background. These are not small successes. They represent genuine, deep understanding. But success in some areas does not immunize a theory against failure in others. And the areas where the standard model is now struggling are not peripheral. They are central. The age of the universe, the rate of its expansion, the formation of the first galaxies, the growth of the first black holes, the behavior of dark matter across cosmic time, these are not footnotes. They are the main text. Several revisions are being seriously considered. The universe may be older than 13.8 billion years. Even a modest upward revision of the cosmic age could dissolve many of Webb's most troubling discoveries. Galaxies would have more time to grow, black holes more time to accumulate mass, heavy elements more time to be forged and distributed. The number 13.8 is not sacred. It is a measurement derived from a chain of assumptions, some of which Webb is now straining. If the Hubble constant changes, the cosmic age changes with it. Dark matter may behave differently than the cold dark matter model assumes. The evidence for some form of dark matter remains overwhelming. the rotation curves of galaxies, the structure of the cosmic web, the dynamics of galaxy clusters all require more gravitating mass than visible matter can provide. But cold dark matter, the specific version that dominates most cosmological simulations, is not the only possibility. Warm dark matter, fuzzy dark matter, and self-interacting dark matter are all being taken more seriously in the light of Webb's clustering data, rotation anomalies, and bullet cluster observations. Each variant predicts different behaviors at small scales and in the early universe. The data is beginning to favor alternatives. Gravity itself may need revision at cosmological scales. Modified gravity theories, which alter the standard equations of general relativity at low accelerations or large distances, have long been considered fringe ideas. They are moving closer to the mainstream as mounting anomalies make the standard gravity plus cold dark matter combination less satisfying. Some versions can explain rotation curves, galaxy clustering patterns, and aspects of the Hubble tension without introducing exotic unseen matter. Cosmic inflation, the theory that in the first tiny fraction of a second after the Big Bang, the universe underwent an explosive expansion faster than light, is under fresh scrutiny. Inflation was proposed in the 1980s to solve several puzzles of standard Big Bang cosmology, and it succeeded remarkably. But the early universe web is revealing, turbulent, fast-developing, structurally advanced beyond expectation, does not match the gentle, smoothly seeded post-inflation cosmos the simplest inflation models predict. A team in Switzerland recently reviewed dozens of inflation models and found that none precisely matches what Webb is showing. Some researchers are exploring whether inflation was more violent or uneven than assumed, whether it ended in different ways in different regions, or whether it even occurred in the simple single episode form the textbooks describe. The most far-reaching possibility is the most humbling. We may be entering an era where existing tools, the equations, the models, the assumptions, are no longer sufficient to describe what we are observing. This has happened before in physics. The discovery of quantum mechanics in the early 20th century forced a complete reconstruction of the rules governing matter at small scales. The discovery of general relativity replaced centuries of Newtonian gravity with an entirely different geometric framework. Each time, the new framework did not destroy the old one. It absorbed it as a special case, while extending physics into territory the previous framework could not map. Webb may be producing the data that forces a similar extension in the 21st century, not a rejection of modern cosmology, but a recognition that it is incomplete, and that the incompleteness is large enough to require something genuinely new. This is not a sign of failure. It is how science advances. The history of physics is a history of models that worked brilliantly until they met observations they could not accommodate. Anomalies are how revolutions begin. The fact that Webb is producing anomalies at a rate no previous telescope has matched is not alarming. It is extraordinary. It means the universe is richer and stranger than our current language of physics can fully describe. What scientists are still working to understand covers almost every area Webb has examined. The Hubble tension shows no sign of resolving without new physics. The mechanism that produced supermassive black holes in the first billion years remains unknown. Whether population 3 stars formed in the way theories predict, or existed in some completely different form, remains an open question. Whether the rotation asymmetry of galaxies reflects a genuine cosmic directional preference, and if so, what caused it, has not been established. Whether the biosignature candidates on K218b reflect biological chemistry or some unusual abiotic process is still under investigation. Whether the icy moons of the outer solar system harbor life in their hidden oceans remains one of the most profound open questions in all of science. New telescopes are being planned and built. Future missions will follow up on Webb's most puzzling discoveries with even greater sensitivity. The Nancy Grace Roman Space Telescope will survey vast areas of sky, providing statistical samples large enough to test the clustering and rotation anomalies with new precision. Ground-based extremely large telescopes now under construction will probe exoplanet atmospheres with complementary methods, potentially confirming or ruling out biosignature candidates. Space missions to Europa and Enceladus are in development that may one day sample their oceans directly. The next decade in astronomy will not be quiet. Webb has opened a window that cannot be closed. The universe has been revealing itself with a clarity and complexity that previous generations of scientists could barely imagine. And what it is showing is a cosmos that does not quite match the one we thought we understood. The early universe was faster, more structured, more chemically advanced, and more extreme than the standard model predicted. The cosmic timeline may be wrong. The behavior of dark matter may be wrong. The physics of black hole growth may be wrong. The distribution of the first stars may be wrong. The expansion history of the cosmos may be wrong. All of these could be wrong in different degrees, pointing toward a single underlying revision in how we understand the universe's most fundamental ingredients and their behavior across time. That revision has not yet been written. The data is still coming in. Webb continues to observe. Every new image, every new spectrum, every new measurement adds to a picture that is simultaneously more detailed and more mysterious than the one it is replacing. What the universe truly is, its full history, its correct age, the nature of the dark matter and dark energy that fill it, the physics that governed its infancy, we are only beginning to see. If these questions fascinate you the way they fascinate the scientists working to answer them, consider subscribing to stay connected with the discoveries as they unfold. The story of the cosmos is being rewritten in real time, and we are only at the beginning. Consider what it means to look at an object 13 billion light-years away. The light that enters Webb's mirror right now left its source when the universe was less than 1 billion years old. The galaxy that emitted it has been gone in its original form for billions of years. What we see is not the galaxy as it is. It is the galaxy as it was, a fossil of light, frozen in the moment of its emission, traveling through expanding space for an incomprehensible duration, before arriving at a mirror no larger than a dining room table, floating in the darkness beyond Earth's atmosphere. This is what makes cosmology different from almost any other science. We cannot visit the objects we study. We cannot run experiments on them. We can only collect the light that falls on us from across the void and try to reverse engineer from that light what the universe looked like when it was sent. Every discovery Webb makes is an exercise in forensic reconstruction across scales of time and space that have no human analog. And the evidence being recovered is not telling the story anyone expected. The standard model of structure formation begins with quantum fluctuations. In the first fractions of a second after the Big Bang, quantum mechanical uncertainty produced tiny density variations across the newborn universe. These fluctuations were stretched to macroscopic scales by cosmic inflation. When inflation ended, these density variations were baked into the fabric of space as the seeds from which all future structure would grow. Over the next hundreds of millions of years, regions of slightly higher density attracted more matter through gravity. Hydrogen and helium accumulated. Eventually, gas clouds began to collapse under their own weight. Stars ignited. Galaxies formed. Clusters of galaxies assembled along filaments of dark matter. The cosmic web began to take shape. In this model, the process is orderly, hierarchical, and slow. Small things come before large things. Simple things come before complex things. The universe's first 500 million years should be its most boring, a dim fog gradually growing its first faint pinpricks of light. Webb is showing a completely different picture. The universe's first 500 million years was not boring. It was explosive. It was advanced. It was building structures that the standard model says required much more time. The question of why this is happening has several possible answers, and scientists are actively debating each of them. One possibility centers on the nature and behavior of dark matter in the early universe. Dark matter is the dominant gravitating substance in the cosmos. It outweighs visible matter by about 5-to-1. It is the cosmic architect, shaping the web of filaments and clusters inside which galaxies form. In the standard model, dark matter is cold. Its particles move slowly and clump easily. This produces a universe that builds structure from the smallest scales upward. But if dark matter is not perfectly cold, if its particles have some thermal velocity, some tendency to smooth out rather than clump, then the earliest structures could look different from what the cold model predicts. Warm dark matter produces fewer small structures and more large ones. Its halos form differently, its filaments connect differently, and critically, galaxies forming inside warm dark matter halos might reach maturity faster at certain mass scales. Some researchers argue that warm dark matter fits Webb's observations better than cold dark matter does. Others dispute this. The debate is active and unresolved. Fuzzy dark matter is an even more exotic alternative. In this framework, dark matter particles are ultralight, so light that they behave quantum mechanically at macroscopic scales, with wave-like properties that suppress structure below a certain characteristic length. Fuzzy dark matter halos have smooth, gently declining density profiles. They produce fewer small galaxies. They alter the relationship between galaxy mass and dark matter content in ways that may better match what Webb is observing in the early universe. Again, the evidence is suggestive but not yet definitive. Self-interacting dark matter allows particles of dark matter to scatter off one another. This changes how dark matter halos respond to collisions between galaxies and to their own internal gravitational dynamics. The bullet cluster, one of the most important objects in the dark matter debate, is now being re-examined through Webb's infrared eyes. The bullet cluster formed when two massive galaxy clusters collided more than 3 billion years ago. The collision separated the visible matter, mostly hot gas that interacted electromagnetically and slowed down, from the dark matter, which passed through largely unaffected. This separation provided one of the strongest pieces of evidence for the existence of dark matter in the first place. Webb's new observations of the bullet cluster reveal that the dark matter distribution is subtler and more textured than previous measurements suggested. Some regions show unexpected clumping. Some boundaries between dark matter zones are sharper than cold dark matter simulations predict. A team at Stanford reanalyzed the structure using Webb's data and concluded that self-interacting dark matter fits the observed distribution better than the standard cold model. The finding is preliminary but significant. If dark matter particles interact with each other during cluster collisions, then the entire framework for modeling galaxy cluster dynamics needs adjustment. The possibility that dark matter has not one simple character, but a more complex behavior, something between these alternatives or something entirely different, is no longer a fringe idea. Webb is providing data precise enough to distinguish between models, and some of the data is pointing away from the simplest version of cold dark matter. Beyond the nature of dark matter, there is the question of what the very first stars were actually like. Population 3 stars, the theoretically predicted first generation, have been described as the universe's most important unknown objects. They shaped everything that came after. Their explosions produced the first heavy elements. Their radiation drove the first phase of reionization, burning away the neutral hydrogen fog that filled the universe before galaxies lit up. Their remnants may have seeded the first black holes. They are as fundamental to the story of the cosmos as any object that has ever existed, but they have never been seen. The theoretical picture of population 3 stars was constructed by astrophysicists working in the 1980s and 90s, using the physics of gas cloud collapse in an environment without heavy elements. The predictions are stark. These stars should have been enormous, possibly hundreds or even 1,000 times the mass of the Sun. They would have burned at temperatures far exceeding modern massive stars. They would have emitted enormous amounts of ultraviolet radiation. They would have lived only a few million years, a cosmological instant, before exploding as parent stability supernovae, a type of explosion that destroys the star entirely and leaves no compact remnant. If this picture is correct, Webb should be able to detect their signatures in the earliest galaxies. The ionized gas around such massive hot stars produces very specific spectral patterns. The chemical enrichment from their explosions leaves distinctive fingerprints. Webb has searched for these patterns. The searches have returned weaker results than expected. This opens several uncomfortable possibilities. Population 3 stars may have been smaller than theory suggests, perhaps only a few times more massive than modern large stars, rather than hundreds of times. This would make them cooler, longer-lived, and far harder to detect. They would still have had unusual chemistry compared to later generations, but they would not have produced the dramatic spectral signatures models predicted. Alternatively, population 3 stars may have formed in smaller numbers and in more isolated pockets of the early universe than anyone assumed. Their collective contribution to reionization and heavy element enrichment might have been far smaller than models require, with the bulk of early cosmic enrichment coming from a second generation of stars that formed rapidly from whatever trace enrichment the first generation provided. Or the models themselves may be fundamentally wrong about the conditions under which the first stars formed. The early universe's gas chemistry was simple, but simple does not mean easy to model. Turbulence, magnetic fields, rotation, and the interplay between gas cooling and heating channels may have produced conditions very different from the clean theoretical picture. Perhaps population 3 stars formed in a distributed, low-mass mode that current theory does not capture. Whatever the answer, the absence of detected population 3 signatures is itself scientifically significant. It is constraining the possibilities. It is forcing theorists to revise the models. And it is revealing that the universe's first chapter may have been written in a language different from the one we expected. The cosmic dawn, the era of reionization when the first stars and galaxies burned away the neutral hydrogen fog, is supposed to be one of the best understood epochs in cosmological history. It is one of the primary science targets for which Webb was specifically designed, and it is producing more surprises than almost any other area of research. Reionization should have been a gradual process in the standard model. Faint, scattered clusters of early stars slowly ionizing the hydrogen around them. The transition from neutral to ionized hydrogen should have taken hundreds of millions of years, spreading smoothly outward from early galaxies. The universe should have lit up gently. Webb is showing that it lit up aggressively and unevenly. Pockets of intense star formation blazed while vast neighboring regions remained dark for much longer. The pattern is patchy and irregular, more like a fire spreading through dry grass with erratic wind than a candle slowly illuminating a room. This kind of irregular reionization is difficult to explain. The standard model's smooth predictions do not match the data. Something drove early galaxies to concentrate their star formation in violent bursts, with pauses and quieter periods in between. One theory connects this to the feedback from the galaxies themselves. When massive stars explode, they drive powerful winds that push surrounding gas outward. In a small galaxy, this feedback can shut down star formation entirely for a period. Then, when the expelled gas cools and falls back, it triggers a new burst. This cycle of burst and quench may be responsible for the patchy, intermittent character of early reionization. But reproducing the observed pattern in simulations requires assumptions about feedback efficiency that current models struggle to support. Another theory invokes the role of early quasars, the intensely luminous cores of early galaxies powered by feeding supermassive black holes. Quasars emit enormous amounts of ionizing radiation that can illuminate large volumes of surrounding space. If the early universe contained more quasars than expected, their collective radiation could have driven an early, aggressive phase of reionization, even before the galaxy population was large enough to do so on its own. Webb has confirmed that quasars existed as early as 700 to 900 million years after the Big Bang. Some appear even earlier. These objects are fully developed quasars, powered by black holes weighing hundreds of millions to billions of solar masses, shining with luminosities hundreds of times greater than entire galaxies. Their existence at such early times is itself a separate crisis for the standard model, connecting back to the black hole growth problem described earlier. But their numbers and their radiation output may be part of the explanation for why reionization proceeded so aggressively. The quasar seed problem is one of the most pressing open questions Webb has brought into focus. How did black holes grow massive enough to power quasars before the universe was even a billion years old, And why does the gas chemistry around early quasars already show signs of heavy element enrichment at levels that require prior generations of stellar evolution? The picture that emerges from all of these threads is one of a universe that was extraordinarily productive in its earliest phase, producing stars, black holes, heavy elements, and large-scale structure far faster and more efficiently than the standard model allows. This productivity may reflect physical conditions specific to the cosmic dawn, conditions so extreme and so different from anything accessible today that current equations fail to capture them accurately. This brings up a possibility that is gaining increasing traction in theoretical physics. The early universe may not have followed the same physical rules as the universe today. This is not as radical as it sounds. The universe's properties have evolved. Its temperature has dropped by a factor of more than 1,000 since the first light elements formed. Its density has decreased by many orders of magnitude. The ratio of photons to baryons has been essentially fixed since the first few minutes, but the character of the gravitational potential wells in which matter collected has changed profoundly over cosmic time. Dark energy, which now dominates the energy budget of the universe and drives its accelerating expansion, was negligible in the early cosmos. If dark energy is not a simple cosmological constant, if it is instead a dynamic field that evolves over time, then the effective physics of cosmic expansion would have been different in the early universe. Some models of dynamic dark energy predict behaviors in the early cosmos that differ significantly from the standard cosmological constant model. Webb's measurements of galaxy clustering and the cosmic expansion rate at various distances are beginning to constrain these models. Early results suggest that the data may favor a dark energy that has changed in character over cosmic history, though the evidence is not yet conclusive. The Vera Rubin Observatory, now entering operation, will soon provide the largest systematic survey of galaxy positions and distances ever compiled, covering billions of objects across vast cosmic volumes. Combined with Webb's deep observations of the early universe, the combined dataset will be powerful enough to distinguish between competing dark energy models with unprecedented precision. The coming years will be transformative for this question. The nature of dark energy, what it is, whether it is truly constant, whether it represents an unknown field or a modification of gravity at cosmic scales, is the biggest open question in physics today. The cosmological constant, introduced by Einstein as a term in his equations of general relativity, provides a simple mathematical description of dark energy, but offers no physical mechanism. Why should empty space have energy? Why does that energy have the value it does, apparently fine-tuned to enable galaxies to form before dark energy's repulsion drives them apart too quickly? These questions remain unanswered. Webb is not designed to answer them directly, but by providing the most detailed picture ever assembled of how the universe evolved, galaxy by galaxy, epoch by epoch, chemical element by chemical element, it is building the observational foundation on which future answers will rest. There is also the question of what comes next for the telescope itself. Webb was designed for a minimum 10-year mission. The precision of its launch trajectory consumed far less fuel than anticipated, suggesting it may operate for 20 years or more before fuel constraints limit its ability to maintain position. This means the discoveries discussed here represent only the beginning of what Webb will find. With each passing year, the telescope's archive of deep field observations grows richer. Statistical samples that currently contain dozens of anomalous objects will grow to hundreds. Patterns that are currently suggestive will become statistically unambiguous. Questions that currently have multiple possible answers will narrow towards single explanations. The TRAPPIST-1 system, the collection of 7 rocky planets orbiting a small red dwarf star just 40 light-years away, will continue to be among Webb's most closely watched targets. 3 of these planets sit within the habitable zone, the range of orbital distances where liquid water could theoretically exist on a planetary surface. Webb has already determined that the innermost planets lack significant atmospheres, reducing their habitability prospects, but the outer planets remain. TRAPPIST-1D, TRAPPIST-1E, TRAPPIST-1F, and TRAPPIST-1G are subjects of ongoing observation campaigns. TRAPPIST-1E in particular has drawn attention based on preliminary data suggesting it may retain a substantial atmosphere. If confirmed, TRAPPIST-1E would immediately become one of the most scientifically significant worlds ever identified. An atmosphere on a rocky planet in the habitable zone of a nearby star would provide Webb with the opportunity to search for biosignatures, chemical indicators of biological activity, in a system close enough to observe in considerable detail. The molecules of interest include not only oxygen and methane, which could have both biological and geological sources, but also more specific indicators like nitrous oxide, which is produced overwhelmingly by biological nitrogen cycling on Earth, and dimethyl sulfide, which echoes the K2-18b discovery. The detection of even one confirmed biosignature on any world outside Earth would be the most transformative scientific discovery in human history. Webb may not make that discovery. It may require future telescopes with larger collecting areas and greater spectroscopic sensitivity, but it may provide the first compelling evidence that points the way. The question is no longer whether such a detection is possible in principle. The question is which world will provide it first. The universe Webb is showing us is stranger than the one we thought we understood. Its earliest galaxies formed too fast, grew too massive, organized too quickly, and forged their heavy elements in compressed timeframes that stretch the known physics of stellar evolution. Its black holes appeared too early and grew too large for the time available. Its cosmic background radiation, once considered the cleanest possible data source, is producing tensions with what the telescope actually finds in the galaxies that grew from that primordial light. Its dark matter scaffolding may not be the simple cold dark matter the simulations assumed. Its first stars may have been different in character from anything the models predicted, and the universe's expansion rate cannot be measured twice and get the same answer. Every anomaly, taken alone, could be a measurement error, a calibration artifact, a systematic bias waiting to be identified. But taken together, after years of cross-checking and independent confirmation, these anomalies are resistant to such dismissal. They are real. The universe is not cooperating with the model built to describe it. That is not a crisis. That is science working exactly as it should. Every major advance in physical understanding began with something that didn't fit. The precession of Mercury's orbit didn't fit Newtonian gravity until Einstein resolved it with general relativity. The stability of atoms didn't fit classical electromagnetism until quantum mechanics provided a new framework. The apparent recession of distant galaxies didn't fit the assumption of a static universe until Hubble's measurements established cosmic expansion and Lemaitre's theory described its origin. In each case, the anomaly was not the failure of science. It was the edge of science, the frontier where the known gave way to the unknown, and where new understanding was waiting to be built. Webb is finding the edge of the current model. It is measuring where the map ends and the unmapped territory begins. What lies in that territory? What new physics? What revised framework? What deeper understanding of the cosmos is not yet known? The equations that will describe it may not yet have been written. The theorists who will write them may still be students, studying the anomalies Webb is accumulating and wondering what kind of universe could produce them. What we can say with confidence is that the cosmos is more complex, more rich, and more surprising than any previous generation of scientists was equipped to discover. Webb has given us the tools to see this complexity clearly for the first time, and every new observation brings into sharper focus the outlines of a universe that is, in some fundamental way, not the one we thought we were living in. The universe is telling a different story than the one we wrote for it. We are only just beginning to learn to read it. There is something almost philosophical about what Webb is doing that goes beyond the specific discoveries themselves. For most of human history, the night sky was simply the night sky, a fixed backdrop of stars, familiar and unchanging on any timescale a human life could perceive. The idea that the pinpoints of light visible to the naked eye were themselves vast suns, that many of them were larger and more luminous than our own, only entered common understanding relatively recently. The idea that galaxies beyond our own existed, each containing hundreds of billions of stars, was not confirmed until the 1920s. The idea that the universe had a beginning, that it had been expanding since an initial state of extreme density and temperature, was not established until the middle of the 20th century. Each expansion of our understanding came with its own wave of vertigo, the realization that the universe was larger, older, stranger, and more indifferent to human scale than the previous generation had imagined. Webb is producing another such wave. The universe is 13.8 billion years old, or perhaps somewhat older, if the Hubble tension is telling us something real about the cosmic timeline. It contains approximately 2 trillion galaxies within the observable volume, each hosting between millions and hundreds of billions of stars. The observable universe extends 46 billion light-years in every direction, despite the universe being only 13.8 billion years old, because space itself has been expanding the entire time, and the most distant light we can now detect has been carried farther by that expansion since it was emitted. Beyond the observable universe lies an unknown extent of cosmos that light has not had time to reach us from, and that we cannot in principle ever directly observe regardless of what telescopes we build. The universe may be infinite, it may be finite but unbounded, it may be one of many, embedded in a larger structure that has no edge and no center and no observable signature accessible from inside. These questions are not new, but Webb is making the portion of the universe that we can study more challenging to understand, which means the portion beyond our reach is even less constrained than we thought. Every assumption we make about the universe at large is built on the assumption that the observable portion is representative, that what we can see reflects the statistical behavior of what we cannot. If the observable universe is behaving in unexpected ways, that uncertainty propagates outward. There is also the matter of timing. The James Webb Space Telescope represents the culmination of decades of scientific planning, political negotiation, engineering challenge, and institutional commitment. Its budget reached approximately 10 billion United States dollars. Its development stretched across more than 25 years. It was designed by an international collaboration spanning multiple space agencies and hundreds of research institutions. When it launched in December of 2021 and began its first observations in 2022, it represented one of the largest cooperative scientific investments in human history. And immediately upon turning on, it began producing data that challenges the foundation of the models that motivated its construction. This is not ironic. It is the expected result of building a better instrument. Every generation of telescope has revealed that the previous generation's understanding was incomplete. Galileo's refractor showed that Jupiter had moons, that Venus had phases, that the Sun had spots, all contradicting the dominant cosmological framework of his time. The Hubble Space Telescope resolved Cepheid variables in distant galaxies with enough precision to confirm that the universe was expanding and to begin measuring the rate, only to discover the Hubble tension when ground-based telescopes later measured the same quantity and got a different answer. Webb, like every instrument before it, was built on the best available understanding and has begun to exceed it immediately. This is science functioning correctly. What makes Webb's situation distinctive is the breadth of the challenge. Previous telescopes tended to push the boundaries in specific, targeted directions. Webb is pushing on almost every direction simultaneously. Its infrared sensitivity gives it access to the most distant observable galaxies, the earliest cosmic epochs, the atmospheres of temperate worlds around nearby stars, the chemistry of icy solar system bodies, the detailed properties of individual stars in nearby galaxies, and the physical conditions within molecular clouds where new stars are currently forming. It is a generalist of extraordinary power, and in nearly every domain it has examined, it has found the universe behaving in ways that were not fully anticipated. The rotation curves of early galaxies are more diverse than expected. The clustering of early galaxies does not match cold dark matter simulations cleanly. The standard candles used to measure cosmic distances, Cepheid variables, and type Ia supernovae may have subtle properties that differ between galaxies with different ages and chemical histories, introducing systematic errors into the cosmic distance ladder. This matters enormously because the distance ladder is the foundation of the Hubble constant measurement, which in turn determines the cosmic age and the nature of dark energy. If the rungs of the ladder are slightly off, everything built on top of it is slightly off. Webb's high-resolution observations of Cepheid variables in distant galaxies are revealing that these stars behave in ways that differ subtly from nearby examples. The pulsation period and luminosity relationship that makes Cepheids useful as standard candles appears to have a dependence on the host galaxy's metallicity, its overall chemical enrichment, that previous, lower-resolution observations could not detect. This is not a large effect, but in cosmology, small systematic effects accumulate. A team at the University of Chicago analyzed Webb's Cepheid data and concluded that the metallicity dependence could account for a few percent of the Hubble tension, not all of it, but enough to matter. Type Ia supernovae, the exploding white dwarfs that serve as the cosmic distance ladder's longest rung, are also under scrutiny. These objects were thought to be highly standardizable. Their peak luminosity, after a simple correction for the shape of their light curve, should be the same regardless of where or when they occur. Webb's higher resolution data is revealing that subtle variations exist in how these supernovae behave depending on the age and chemical composition of the stellar populations that produce them. Old, metal-poor stellar populations produce supernovae with slightly different properties than young, metal-rich ones. In the early universe, where stellar populations are systematically different from those nearby, this could introduce biases into distance estimates. None of this means the distance ladder is broken. It means it is being refined with new tools. The refinement may end up tightening the Hubble constant, or it may reveal that the local expansion rate is genuinely different from what the early universe predicts, confirming that new physics is required. This ongoing process of measurement and refinement is what science looks like from the inside. It is not a series of clean eureka moments. It is a slow, careful accumulation of evidence, argument, counter-argument, reanalysis, and gradual consensus. The discoveries Webb is producing will be debated for years before the field converges on their implications. Some anomalies that currently appear real will turn out to be systematic errors. Others that currently appear marginal will be confirmed and will reshape the model. The process is neither fast nor tidy, but it is reliable. The history of cosmology is a history of this process working, of instruments seeing farther, of models being extended, of the universe gradually revealing itself in ways that each generation of scientists used the previous generation's framework to begin understanding and then exceeded. We are in that process now, with Webb as the instrument at the frontier. What can be said with confidence at this stage is that the universe is not the relatively simple system that the lambda CDM model describes. It is more complex, more dynamic, more structurally surprising in its early epochs, more chemically advanced at early times, and more varied in its dark matter behavior than the simplest version of the standard model accounts for. The revision that will eventually emerge from Webb's discoveries, whether it takes the form of modified dark matter physics, revised inflation models, adjustments to the cosmic age, or something more radical, will not come from any single paper or any single observation. It will come from the gradual convergence of many lines of evidence, each one tested independently and cross-checked against the others. The galaxy too massive for its age, the black hole too large for the time available, the spiral disk too organized for the violence of the early cosmos, the heavy elements too abundant for the stellar generations required to produce them, the rotation asymmetry with no preferred direction in the standard model to explain it, the biosignature candidate on a world 120 light-years away, the oldest single star ever resolved, burning against the void of the early universe with properties no modern star shares, the cosmic expansion rate that gives two different answers, the ancient light of the cosmic microwave background no longer perfectly mapping onto the galaxy distribution that grew from it. Each of these is a question. Taken together, They are a conversation between the universe as it is and the universe as we thought it was. Webb is translating that conversation, one observation at a time, and the translation is revealing a cosmos that is richer, stranger, more complex, and more interesting than the one described in any textbook currently in print. That is reason enough to keep looking, to appreciate the full weight of what Webb is accomplishing. It is worth stepping back to consider the history of instruments that preceded it. The first systematic telescopic observations of the sky were made in the early 1600s. Within a generation of Galileo's first observations, the heliocentric model of the solar system, Earth orbiting the Sun, not the reverse, became undeniable. Within 2 more generations, Newton's laws of gravity unified the motion of falling objects on Earth with the orbital motion of planets, and provided the mathematical framework that would govern astronomy for the next 2 centuries. In the 20th century, the pace accelerated dramatically. Edwin Hubble's measurements of Cepheid variable stars in the Andromeda Galaxy in 1924 proved that it lay far beyond the Milky Way, that our galaxy was not the entirety of the universe, but merely one of many. His subsequent discovery that distant galaxies were receding at velocities proportional to their distances established that the universe was expanding. Georges Lemaître connected this expansion backward in time to an initial state of extreme density, what we now call the Big Bang. The detection of the cosmic microwave background radiation in 1965 by Penzias and Wilson provided direct observational confirmation that the universe had indeed passed through a hot, dense early phase. Then came the second great wave of 20th century cosmology. The Hubble Space Telescope, launched in 1990, brought the universe into focus with a precision ground-based telescopes could not match. It resolved individual stars and galaxies tens of millions of light-years away, refined the cosmic distance scale, observed the expansion history of the universe through supernovae, and produced the famous Hubble Deep Field images that first revealed the sheer abundance of galaxies across cosmic time. In the late 1990s, 2 teams studying distant supernovae discovered independently that the universe's expansion is not slowing under gravity, but accelerating, driven by an unknown energy component that came to be called dark energy. This discovery, which earned its leaders the Nobel Prize in Physics in 2011, fundamentally altered the standard model of cosmology and remains unexplained at a deep physical level. The cosmic microwave background was mapped with increasing precision by the COBE satellite in the early 1990s, the WMAP satellite through the 2000s, and the Planck satellite through the 2010s. Each measurement refined the standard model, tightened the parameters of the lambda-CDM framework, and appeared to confirm the cosmological picture. By the time of Planck's final data releases, cosmologists spoke of a standard model so well tested that its major features seemed settled. Webb has arrived at this moment of apparent settlement and found that the settlement was premature. The irony is precise. The more powerful the instrument, the more clearly the anomalies become visible. The Hubble Deep Field images from 1995 first suggested that the distant universe contained more galaxies than expected. Webb's deep fields show that those distant galaxies are also more massive and more structured than expected. The trend was already there, waiting for a more powerful telescope to bring it into undeniable focus. The missing satellites problem, the discrepancy between the number of small dwarf galaxies that cold dark matter simulations predict and the smaller number actually observed, has been known for over 2 decades. Webb's deep observations of the early universe, where small proto-galaxies should be most abundant, found the early cosmos less crowded than simulations demand. The problem is not new, it is deeper. The tension between local and early universe measurements of the Hubble constant was first flagged as a potential problem in the early 2010s. It has been sharpening ever since, with every new measurement adding to the tension rather than resolving it. Webb's Cepheid data has refined the local measurement without closing the gap. The question of how supermassive black holes formed so quickly in the early universe has been posed since the discovery of high redshift quasars in the 1990s. Webb has found that even more extreme examples exist at even earlier times than previously known. The problem is not new, it is more acute. This pattern suggests something important. The anomalies Webb is revealing are not new problems created by the telescope. They are old problems that previous instruments lacked the sensitivity to expose clearly. Webb is not finding a new universe. It is finding the same universe in enough detail to reveal what the coarser instruments could not resolve. That distinction matters because it suggests the revisions ahead are not superficial. If these anomalies had appeared only at the sensitivity threshold of a new instrument, they might represent something exotic and rare. But appearing as amplified versions of tensions and discrepancies that have been nagging the field for decades, they suggest instead that the underlying standard model has been straining against the observations for years, and that Webb's sensitivity is finally making that strain impossible to rationalize away. The field of cosmology stands at one of its periodic turning points. The last such turning point came with the discovery of dark energy in 1998, which required adding an entirely new component to the cosmic inventory, something that makes up about 68% of the total energy density of the universe, yet produces no detectable emission, has no known physical mechanism, and cannot be derived from first principles in any currently accepted theory of physics. The turning point before that came with the confirmation of dark matter, the recognition that roughly 27% of the universe's energy density is composed of matter that interacts gravitationally but not electromagnetically, that has never been directly detected despite decades of effort, and whose particle identity remains completely unknown. In both cases, the standard model accommodated the new discoveries by adding ingredients without fully explaining them. Dark matter and dark energy are placeholders, labels for things that are observed to have certain effects without any understanding of their fundamental nature. The lambda CDM model works not because it explains dark matter and dark energy, but because it describes their gravitational effects accurately enough to match most observations. Webb may be revealing that the description, even at this level, is not quite accurate enough, that the effects attributed to dark matter do not precisely match what the telescope is observing in early galaxies and galaxy clusters, that the cosmic history described by the standard model does not precisely match what Webb is finding in the earliest observable epochs. If that is the case, the next step is not simply to add another ingredient to the cosmic recipe. It may require reconsidering the recipe itself, asking not just what the universe contains, but whether the equations used to describe how those contents interact are correct. This is the deepest level at which science operates. Adjusting constants within a framework is common. Extending a framework to include new phenomena is less common but well established. Replacing the framework itself, revising the fundamental equations of gravity, or the principles of quantum field theory, or the relationship between space, time, matter, and energy, is rare and difficult and consequential. Whether Webb's discoveries require this level of revision is not yet known. The data being collected right now, the analyses being conducted in universities and research institutes across the world, the papers being written and reviewed and debated, all of these are working toward an answer. The answer may take years to emerge. It may take decades. The history of physics suggests that major conceptual revisions rarely arrive cleanly or quickly. They come gradually, through the accumulation of evidence and the slow erosion of the assumptions that prevented the new framework from being recognized sooner. What Webb is doing is accelerating that accumulation. Its observations are arriving faster, going deeper, covering more of the sky, and resolving finer details than anything before it. The rate of discovery is genuinely unprecedented, and with each new discovery, the contours of whatever understanding will eventually replace or extend the current standard model come into slightly sharper focus. The universe is communicating. It has been communicating since the first light from the first stars crossed the void between galaxies and entered the atmosphere of a small rocky planet where, over the course of billions of years, matter organized itself into creatures capable of building instruments sensitive enough to detect what was being transmitted. Webb is the most sensitive receiver humanity has yet constructed for that transmission. What it is hearing is a universe that is not quite what we thought, a universe whose early chapters were more turbulent, more productive, and more structurally advanced than our equations predicted. A universe whose dark components, the matter and energy that dominate its gravitational dynamics and its expansion, may behave differently than the simplest models assumed. A universe whose expansion history contains a contradiction that has survived every attempt at resolution. A universe whose oldest visible light carries anomalies that were previously invisible to us. And a universe that may harbor, in the cold liquid depths beneath ice shells on moons within our own solar system, and in the atmospheres of worlds orbiting stars dozens of light years away, the beginnings of an answer to the most personal question the cosmos can pose. We are looking, we are listening, we are learning. And the universe, for all its indifference to scale and all its disregard for human expectations, is answering. One thread worth pulling before closing this journey through Webb's discoveries is the question of what the telescope's findings mean for the search for extraterrestrial intelligence. The search for life beyond Earth typically divides into two distinct programs. The first searches for microbial or simple biological life, biosignatures in planetary atmospheres, chemical indicators of metabolism, the building blocks of biochemistry on distant worlds. The second, more speculative program searches for signs of technologically sophisticated civilizations, radio signals, laser pulses, anomalous stellar energy usage, megastructures, or other artifacts of intelligence operating at scales visible across interstellar distances. Webb is primarily advancing the first program. Its biosignature detections, however preliminary, represent the first real observational leverage on the question of whether life exists on other worlds. But Webb's deeper cosmological discoveries are also relevant to the second program in an indirect way. If the early universe built galaxies, heavy elements, and potentially planets far faster than the standard model predicted, then the cosmic timeline available for the emergence and evolution of complex life may be longer than previously assumed. If rocky planets could form from the dust and heavy elements produced in the first billion years after the Big Bang, which Webb's chemistry discoveries suggest is possible, then life may have had more time to emerge, evolve, and potentially develop complexity than conventional estimates allowed. This pushes the expected distribution of technologically sophisticated civilizations earlier in cosmic history. It also raises a sharpened version of the Fermi paradox, the famous question of why, if intelligent life is possible and has had enormous amounts of time to develop, we see no obvious signs of it anywhere in the universe. Webb cannot address this question directly. Its instruments are not designed to detect the signatures of technological civilizations, but the picture it is building of a universe that was productive and structurally advanced from an early age is relevant context for thinking about when and where life had the opportunity to develop. The discovery of dimethyl sulfide on K2-18b, if eventually confirmed as biological in origin, would establish that life exists within 120 light-years of Earth. That distance is tiny on cosmic scales. It represents a region containing only a few hundred stars out of the 2 to 400 billion in the Milky Way. If life is present this close, the statistical implication is that it is widespread throughout the galaxy. This would not prove the existence of intelligent civilizations, but it would make the conditions for life appear common, and would invite the question of where intelligence has had time to develop and why it has not made itself obvious. These questions are not answered by Webb's current data, but they are shaped by it. The telescope is placing firm observational constraints on where and when the conditions for life first became possible, how common the relevant chemical ingredients are, and how the atmospheres of rocky worlds in habitable zones actually behave. Each of these constraints narrows the range of possibilities and points toward the observations that will eventually settle the question. The generation of scientists now entering research careers will work with Webb's archive, and with the instruments that follow it. Some of them will resolve the Hubble tension. Some will determine the nature of dark matter. Some will map the cosmic web in the early universe with enough detail to definitively rule in or rule out competing models. Some will detect the atmospheric chemistry of a dozen or 100 potentially habitable worlds. and build the statistical database needed to identify genuine biosignatures with confidence. And some, perhaps, will see a signal that has no explanation other than the one that changes everything. The universe is out there, in every direction, at every distance, at every epoch accessible to a sufficiently sensitive instrument. Webb is the most sensitive instrument humanity has ever pointed at it. What it is finding is a cosmos that exceeds our models, defies our timelines, and refuses to fit neatly into the framework we constructed for it. That is not a problem to be solved and forgotten. It is an invitation from the universe itself, transmitted in light billions of years old, received by a mirror the size of a room, orbiting in the cold dark 1.5 million kilometers from Earth. To understand it better, we are answering that invitation. The data Webb collects is not just about individual objects. It is about patterns. And patterns in science are where the deepest understanding is hidden. When a single galaxy is too massive for its age, it could be an error. When dozens are too massive, it is a trend. When hundreds are too massive, distributed across separate regions of the sky, observed through different filters, confirmed by multiple independent teams using different analysis techniques, it is a discovery. And a discovery of this magnitude is not the kind that goes away. It accumulates. It grows sharper. It forces the models to either adapt or fail. The standard model of cosmology has survived for decades precisely because it could adapt. Dark energy was not predicted, but the model absorbed it. The specific properties of dark matter remained unknown, but the model described its gravitational effects accurately enough. The Hubble tension emerged, but for years could be attributed to measurement systematics. Webb has now put enough pressure on enough parts of the model simultaneously that adaptation alone may not be sufficient. The concept of galactic downsizing provides one example of how the model has already been forced to adapt in response to earlier observations. Standard bottom-up structure formation predicted that large galaxies should form late, assembled from smaller predecessors over billions of years. Observations in the early 2000s revealed instead that the largest galaxies, massive ellipticals, had their star formation mostly complete very early, while smaller galaxies continued forming stars much later. This was the opposite of the simple hierarchical prediction. The model was adjusted to accommodate it through a combination of rapid early star formation in massive halos and feedback mechanisms that shut down subsequent star formation. The adjustment worked, more or less, but it required making the model more complex and more parameter-dependent. Webb is now producing observations that strain even the adjusted model. The massive early galaxies it finds are not just large. They are large and organized and chemically enriched, and hosting enormous black holes in a cosmic era that the adjusted model still predicts should be too early for all of this to coexist. The adjustments already made are not enough. There is also the issue of what astronomers call tension between theory and observation at small scales. The standard model, run through computer simulations, makes specific predictions about the internal structure of galaxies and galaxy clusters at scales of a few kiloparsecs and below. These predictions include the density profiles of dark matter halos, how steeply density rises toward galactic centers, and the abundance of substructure within halos. Observations of real galaxies have repeatedly found core density profiles that are flatter than the simulations predict, and fewer small satellite galaxies than expected. These are old problems, but Webb is adding new data that makes them harder to dismiss as measurement artifacts. In the Bullet cluster, Webb's resolved view of the dark matter distribution is showing variation on scales that cold dark matter simulations do not naturally reproduce. In early galaxies, the rotation curves Webb is measuring are too diverse for any single dark matter model to explain. In the cosmic web, the filaments Webb is finding at early epochs are longer and more organized than cold dark matter predicts should be possible. The accumulation is the problem. Any one of these could be a model parameter issue. All of them together begin to look like a framework issue, which brings us back to where this story began. 2 measurements, 2 answers, 1 universe. The Hubble constant measured from the cosmic microwave background gives approximately 67. The Hubble constant measured from local objects gives approximately 73. Webb's contribution has been to sharpen the local measurement, to provide the most precise Cepheid variable data ever collected, and confirm that the local number does not converge toward the early universe number. The tension persists. This means that either the early universe and the late universe are genuinely expanding at different effective rates, which is not possible in the standard model without adding new physics, or our measurement of one or both epochs contains systematic errors that have survived years of scrutiny. Early dark energy is the leading proposal for resolving the tension within the framework of the standard model. This involves postulating an additional energy component that was present in the first 100,000 years of cosmic history and boosted the expansion rate during that era, before fading away and leaving the cosmos in a state that subsequently evolved to produce the universe we see. The effect on the cosmic microwave background is small but calculable. It shifts the predicted Hubble constant upward enough to bring it into agreement with the local measurements. The problem with early dark energy is that it is, in essence, a new ingredient invented specifically to solve this one problem. It has no other motivation from fundamental physics. It must be fine-tuned to have exactly the right magnitude to resolve the tension without conflicting with other observations. And it does not obviously connect to any known physical mechanism, postulating it is scientifically legitimate. This is how the standard model has absorbed surprises before, but it adds complexity without explanation. Alternatively, modified gravity at cosmological scales could resolve the tension by changing the relationship between matter density and expansion rate in a way that makes the two measurements naturally consistent. Modified gravity theories come in many varieties, and most of them face their own challenges in fitting all of the available data. But the Hubble tension is providing them with renewed motivation. A more radical alternative, proposed by a small number of researchers, is that the universe has a large scale inhomogeneity, that our local region of space is embedded in a void or an overdense region whose local expansion rate differs from the global average. If the Milky Way sits in a region of space that is slightly less dense than the cosmic average, the local expansion rate would appear higher than the global rate inferred from the early universe. This is not a new idea, but it has faced skepticism because such a large-scale void would need to be implausibly large to produce the observed tension. Webb is providing data that can test some of these proposals. Its observations of galaxy distributions and clustering at various distances are sensitive to the presence of large-scale inhomogeneities. Its measurements of Type Ia supernovae at high redshifts probe the cosmic expansion history at epochs between the local universe and the epoch of the cosmic microwave background. The coming years of Webb observation will sharpen these tests considerably. Whatever the resolution of the Hubble tension turns out to be, new physics, refined measurements, or some combination, it will have implications that ripple through every other area of cosmology. The age of the universe, the nature of dark energy, the history of cosmic structure formation, and the interpretation of the cosmic microwave background all depend on the value of the Hubble constant. Getting it right matters for everything else. Webb is the best instrument currently operating for constraining the Hubble constant through multiple independent methods. It will not resolve the tension alone, but it is providing the data that the next theoretical synthesis will need to work with. In the meantime, the universe continues. Galaxies continue to form, age, and merge. Stars continue to ignite and explode. Black holes continue to feed and grow. The cosmic web continues to stretch as dark energy drives the expansion of space. The observable universe is growing by 1 light year in every direction every year, as light from previously unreachable sources crosses the expanding horizon and becomes visible for the first time. Every second of Webb's operational life captures photons that have been traveling for billions of years. Every spectrum reveals the chemical signature of a galaxy whose stars burned and died before the sun existed. Every measurement adds another constraint on the parameters of the universe, and increasingly, another challenge to the model that those parameters are supposed to describe. This is the moment we are in, not a moment of settled science awaiting confirmation, not a moment of confusion without direction, a moment of productive, generative tension between what we understand and what we observe, between the model and the universe, between the equations we have and the data that is arriving faster than they can accommodate. It is, in the specific sense that word carries in the history of science, a revolutionary moment. Webb did not cause it. The universe caused it. Webb is simply making it impossible to ignore.